Hi, this is Dr. Mohammad Fizhan Suzal with second lecture on the basics of ECG. In the last lecture, we talked about what different ECG waves represent and how to differentiate between them on the ECG, on the real ECG. In today's lecture, we are going to talk about how different ECG waves are formed, why some of the ECG waves are positive and some of the ECG waves are negative, and we will also talk about different ECG segments, different ECG intervals, their durations, and at the end we will have some practice on the real ECG. So this is electrical representation of one complete heart cycle, and this here is conduction system of the heart. This big arrow, well, this is what this lecture is all about. This is axis of the cardiac vector. In simple terms, this is the direction in which the heart is depolarized. Precisely and technically, this is not correct because different areas of the heart have different axes of electrical vector, meaning they are depolarized in different directions. That's why we have some positive waves and some negative waves. But actually the left ventricle, this left ventricle is the largest of all heart chambers. That's why its electrical vector also dominates all the other electrical vectors, and this is why the cardiac vector as a whole is represented by the electrical vector of left ventricle. Okay, understood? Now, for the sake of simplicity, just remember 2 points. One point is that any impulse, any electrical impulse that travels in the direction of this cardiac vector will produce a positive deflection on the ECG machine and thus positive wave. Okay. Second point is that positive charges moving towards positive electrode. Let's say here is the electrode, we call it exploring lead. Okay, you have heard about lead 1 2 3, AVL, AVR, etc. These are exploring leads. We place it here and it senses the electrical activity of the heart. So positive impulses traveling towards SA node generates impulse which is positive, and it traveling towards the positive electrode will produce a positive deflection and thus positive wave. Similarly, negative charges moving towards negative electrode will also produce positive deflection and thus positive wave. On the other hand, different charges, meaning negative charge moving towards positive electrode or positive charge moving towards negative electrode, will produce a negative deflection. Okay, so SA node, it generates the electrical impulse and the impulse travels in this direction and through the Beckmann's bundle to left side to depolarize left atrium. The impulse generated by the SA node travels downwards to depolarize the right atrium and towards the left atrium to left side to depolarize the left atrium, meaning the impulse is traveling downwards and leftwards. This is also the direction of the cardiac vector, and thus it will produce a positive deflection on the ECG machine and thus positive wave, the P wave. Okay, then the electrical impulse relays in the AV node. We have already discussed in the previous lecture that AV node is a bad conductor. Why it is a bad conductor we will discuss maybe in later lectures, but for now just remember that AV node is a bad conductor and here there is no electrical activity. The ECG machine does not detect any electrical activity here, so the heart is said to be electrically silent for that moment, almost 0.1 second. That's why this this segment here, we call it the PR segment. This is isoelectric, meaning it is neither positive, neither negative, no deflection at all, because the heart is electrically silent. Then the impulse travels down bundle branches. Okay, this is a interventricular septum, this thing here, sorry, this is a interventricular septum, and it is depolarized by the left bundle branch block. This thing, the left bundle branch depolarizes the interventricular septum. But here is the technicality: the interventricular septum is depolarized in this direction, upwards and rightwards. Okay, upwards and rightwards, which is a direction opposite to the cardiac vector, and so it will produce a negative deflection and thus negative wave on the ECG. This negative wave, the Q wave, is the depolarization of the interventricular septum. Okay, now Q wave is small because interventricular septum is also small, meaning it needs only small voltage of current to depolarize completely, and thus the Q wave is also small. Okay, now the electrical impulse travels down the left bundle branch and right bundle branch to depolarize left and right ventricles. The electrical axis of right side is in this direction. Okay, the electrical axis of left side is in this direction. But again, like I said, left ventricle is the largest, and since both ventricles are being depolarized at the same time, the electrical vector of left ventricle dominates. Okay, the electrical vector of left ventricle dominates, and thus it is this, the electrical vector of left ventricle, that shows up on the ECG machine, and thus we have this R wave. The electrical vector of left ventricle is downwards and in this direction, left direction, the direction of the cardiac vector, and that's why we have this positive deflection again. Okay, now the electrical impulse travels here in this area. This area is the basal segment of the heart. Okay, and since the electrical impulse is traveling in this direction, upwards and rightwards, which is opposite to the direction of the cardiac vector, it generates negative deflection on the ECG machine, and thus this negative wave on the ECG paper, that is S wave. S wave represents electrical depolarization of the basal segments of heart. Okay, these are basal segments, and here the impulse is traveling in this direction, which is opposite to the cardiac vector, and thus it is producing negative deflection and thus negative wave. Okay. Now the heart is completely depolarized, meaning no electrical transmission. Thus the heart is electrically silent again, and thus we have this segment, ST segment, which is isoelectric again because there is no current transmission and thus no deflection on the ECG machine. Now it's time for repolarization, and here are some points regarding repolarization. The last part to depolarize these basal segments will be the first to repolarize. Okay, the second technicality is that in repolarization, it's not that the electrical impulse is traveling backwards. No, that's not happening in repolarization. In repolarization, it's just that the cells are becoming negatively charged. Okay, we have read in action potential that in depolarization, sodium ions go in and make the membrane potential positive. That's what happened during depolarization. The cells became positive. Now that the cells are completely positive, the potassium channels will open and potassium ions will go out and make the membrane potential negative. That's what is happening in repolarization. Okay, the cells are just becoming negative charge. Okay, so like I have already mentioned that negative current moving towards the negative electrode will produce what? Positive deflection. Okay, in repolarization cells are becoming negative charge, so negative current will be traveling through the cells, and negative current moving towards negative electrode, here will be the negative electrode, the exploring lead. Negative current moving towards the negative electrode will produce a positive deflection, and thus the positive wave, the T wave is positive. That's how different ECG waves are formed, and that's why some of the waves are positive and some of the waves are negative. That's the whole concept behind positive and negative deflections of the ECG machine, and thus positive and negative waves on the ECG paper. And in a 12 lead ECG, you may have already seen that some of the leads have positive waves and some of the leads have negative waves. Let me show you a 12 lead ECG. Here you can see some of the leads. Lead 1 has positive, QR has positive, but in AVR, all the waves, P wave, QRS and T wave, all of them are negative. Why? Because they are moving in a direction negative to that cardiac vector. Okay, that's how different leads have different directions of the QRS complexes and P wave. Mostly it's just the AVR that has all the negative waves, but sometimes it can also be negative in V1, and the concept is the same that I have already discussed here. Now let's learn about some ECG measurements. Let's suppose this is a piece of ECG paper, and this is x-axis, this is y-axis. Okay, this here is one large box, and this here is, let me try with some other color, this here is one small box. Okay, now one small box on x is equal to 1 mm is equal to 0.04 second. Okay, one small box on y is equal to, again, 1 mm, but on y-axis we have voltage, on x-axis we have time, on y-axis we have voltage. So on y-axis one small box is again 1 mm, but 0.1 millivolt. Okay, one large box on x is equal to 5 mm. 0.04 multiply 0.04 multiply 5 is equal to 0.2 second, and one large box on y is equal to 5 mm, but 0.5 millivolts. Okay, coming back here, this is P wave, and normally P wave duration is less than 0.12 second, almost. Three small squares. 1 small second is equal to 0.04 seconds, so 3 small seconds must be 0.12 seconds. Then we have PR interval. The interval between these two dotted lines is PR interval, and PR interval is is normally somewhere between 0.12 to 0.2 seconds, almost equal to 3 to 5 small squares. Then we have QRS complex. This is QRS complex, and QRS complex is normally between 0.08 to 0.12 second, almost 2 to 3 small squares. Okay, in the last lecture I incorrectly mentioned QRS complex as 0.8 second. Here I have correctly written it. ST segment, we don't actually measure it because it depends on QT interval. When the QT interval in return is inversely proportional to the heart rate. When the heart rate fastens, the QT interval shortens, and when the heart rate slows down, the QT interval lengthens. Okay, QT interval is somewhere between 0.36 to 0.44 second. Anything greater than 0.5 second is dangerous. Okay, almost 8 to 11 small squares. QT inversely proportional to heart rate. That's why we measured QTC, corrected QT interval. There are a lot of formulas which you can search on in the internet, because we have to correlate the QT interval with the heart rate. Okay, so these are the ECG measurements which are essential for correctly interpreting the ECG. So P wave here. P wave I said is less than 0.12 seconds, almost less than 3 small seconds. Here it's almost 2 small seconds, 0.08 seconds. Okay, so it's normal. Now PR interval from here to here, 1 2 3 4 small seconds, almost 0.16 seconds. Normally it's between 0.12 to 0.2 seconds, so 0.16 seconds is completely normal. Okay, now QRS here, normally it's between 0.08 to 0.12 seconds, from 2 to 3 small seconds. Here it's 2 small seconds, 0.08 seconds, so it's also normal. Now QT interval, Q is here and T is here. Okay, 3 5 9 small seconds, almost 0.36 seconds, so it's also normal. So all the intervals are completely normal. That's it for today. I hope you enjoyed this video. See you in the next lesson.